have this one, yikes. I could have this one, and let's see, chlorine, iodine, bromine. Let's do chlorine again, I guess. So I'm disconnecting here, and my other piece is going to be methyl something. So let's pick bromine, iodine, chlorine. Let's do bromine again. Okay. And obviously this is tertiary, so I must make that into the nucleophile. So my cuprate is going to look like this. I'm going to write this as purple to give myself room. Right, so PR is the abbreviation for purple. And then my sequence is going to be the what is it, bromine, chlorine, and this is N purple. And I will do lithium in dry ether. Step 1, step 2, cuprous iodide, step 3, methyl bromide. So I could make this compound 1, 2, 3, 4, 5 different ways by choosing along which carbon bond I disconnect. And this disconnection approach is a very useful one to take when we're doing organic synthesis, and that's particularly true when we're looking at the copper-mediated reaction, or the Corey-Posner-Whitehouse reaction. Okay, so we've looked, and again, so what this reaction allows us to do is that we make alkanes, but we make alkanes that have more carbons than either predecessor. In fact, it has, if you sum the number of carbons in Rx and R prime X, that's what you get in your alkane product. So it allows you to make alkanes, or what we call higher alkanes, because they have more carbons. Okay. So, from haloalkanes, we've made alkanes by zinc acid reduction, also called direct reduction, by going through the alkyl lithium followed by water or D2O or T2O. Neither one of those changes the number of carbons. And then the third method is the Corey-Posner-Whitehouse reaction, which allows you to make a higher alkane. There's a fourth one which we're not going to go into. It's called the Wurtz reaction, but the Wurtz is a little bit clumsy and difficult to control, and so we leave that one out. And then the last method, which we're not going to spend a lot of time on, is from carbonyl compounds, and we will not go into any sort of great detail, and you will in second organic. But I will point out now that if I start off with an aldehyde or a ketone, there are a couple of ways in which we can convert it down into corresponding alkane. So let's say, for example, one was by hydrogenation, 2 was from haloalkanes, and 3 is reduction of carbonyl compounds. And so, as an example, if I have, let's say, ketone or even an aldehyde, if I treat these with amalgamated zinc and conc HCl, I would end up with the corresponding products, where what we're basically doing is we're replacing C double bond O by CH2, so we're getting the corresponding methylene. So I can convert the carbonyl compound, I can reduce it from the aldehyde level down to the alkane level. Aldehyde level down to the alkane level. I could do it that way, or I could use hydrazine in basic hydrazine in ethylene glycol and reflux. This second one, well, in fact, they both have names. The one at the bottom is called the Wolff-Kishner reduction, and the one on the top is called the Clemenson reduction. So I can convert carbonyl compounds, aldehydes or ketones, aldehydes and ketones, into the corresponding methylenes, right? Either by the Clemenson reduction, which is amalgamated zinc dissolved in mercury, if you will, and conjugate Cl, or I can use the Wolff-Kishner reduction. And there are several modifications. We're just going to stick with the classic one, which is basic hydrazine. Hydrazine is rocket fuel. Basic hydrazine refluxed in ethylene glycol, and that gives rise to the corresponding alkane. This one also does not change the number of carbons, right? So the only one that we have that changes the number of carbons is the only one we have that changes the number of carbons is the Corey-Poisson-Whitehouse reaction. Okay, so we have three methods of preparing alkanes. Again, hydrogenation of alkenes and or alkynes. From haloalkanes, two methods that do not change the number of carbons. That's the zinc acid reduction and the method via the alkyl lithium. And then third is the then there's the Corey-Poisson-Whitehouse reaction, which changes the number of carbons. And then the third method is by reduction of aldehydes and ketones. All right. Then the last thing we look at in this series is reactions of alkanes. And again, this is alkanes and cycloalkanes because they are kindred. Okay, so we are only interested in mentioning two reactions of alkanes and cycloalkanes. One is combustion, and then the other is what we call free radical halogenation. Well, I'll write this down. So one is combustion, and the other is free radical halogenation. So of those two reactions, only one of them is of real value to the organic chemist, which is a free radical reaction. In the bad old days, alkanes were called paraffins. Right? Alkanes were called paraffins. And the reason they were called paraffins is because they were without affinity. So para-affinis means that they were without affinity. So they weren't attracted to anything, which means they gave no reactions. They gave very few reactions. So of all the classes of organic compounds that you would meet, the ones that give the lowest reactivity, the ones that give the fewest reactions, are alkanes. Anything with C and H, alkanes for example, will burn. And while burning has value from an industrial perspective, because as a species we still burn the crap out of things as a way of deriving energy. So we burn natural gas in our homes or in labs. We burn liquid petroleum, liquid propane when we're barbecuing. When we're going to do cigarette lighters, we burn butane. The petrol that powers our cars is usually some C5 but some C12 alkanes. And then jet fuel, when you go to 18-wheelers and so on, the diesel and the jet fuel, they get higher and higher numbers of carbons. So fundamentally then, if I look at combustion, so I can take, for example, methane, and methane burns in the presence of oxygen, right? You require some sort of spark, and you get carbon dioxide plus water. And if I were to balance the equation, I'll get two waters, so that's going to be 2O2. So methane burns in oxygen to give carbon dioxide and water. The reaction releases a large amount of energy. Let's call it delta H of combustion 1. So delta H of combustion, I'm going to call that 1. Well, if I use less oxygen, so let's say I took the same methane and I use 1.5 equivalents of oxygen, what I get instead is carbon monoxide plus 2H2O. And that releases delta H of combustion, and we're going to call this 2. Right? So if I were to starve the reaction, instead of getting carbon dioxide, I now get carbon monoxide. And if I were to starve it even more, so just 1O2, what I would get is carbon, in other words, soot, and water. And that's going to release the delta H of combustion 3. And this number is the highest of the lot. So when I do complete oxidation of both the carbon and the hydrogen, I release the most energy, and the most exothermic. And so ideally, if you're burning stuff for energy, this is what you want. So you want enough oxygen coming into the intake, right? So you can do a complete combustion. But when you're starving the system of oxygen, that's when you start making carbon monoxide, which is toxic. And if you even starve it further, you make soot. So often if you're sitting behind an 18-wheeler at a traffic light, and it's suddenly, the guy or the girl suddenly depresses the accelerator. So we're flushing fuel into the combustion chamber, and we're not getting enough oxygen in. At the beginning, there's not complete oxidation. So you see black smoke coming up, and that contains lots of carbon. But eventually, the air intake catches up, and you start doing more complete oxidation. So you start going through the soot, the carbon monoxide, which is not good, and then the carbon dioxide, which is also not good, because that's a well-known greenhouse gas. I will make it a point here, and I'm not going to go on too much of a tangent here, but it's interesting to note that all triatomic molecules are greenhouse gases. And we've watched over the last 100 and something years, the carbon dioxide concentration in the atmosphere has been rising quite steadily. And you can plot carbon dioxide concentration as a function of time from the advent of the Industrial Revolution. And I mean, the data are very clear. We're pumping large amounts of carbon dioxide into the air, and as a result, the parts per million is at a record high. Really has not been this high for, any number of millions of years. And so what that's creating is a greenhouse effect on the planet. And we've seen over the last decade, the temperatures have been the highest they've ever been. Well, the temperatures have been steadily rising on the planet. We eventually will have to find some more feasible method of getting energy rather than burning stuff, because there's a limit to how many things you can burn. These fuels are not renewable. At some point we'll run out of oil and natural gas. And so there's a lot of effort being made in finding alternate sources of energy, sunlight, wind energy, geothermal energy, nuclear energy, that has its own issues. So that's for your generation to kind of solve. Mine certainly screwed it up. But we're looking for alternative paths to generate energy. Okay, so let's set aside combustion It's valuable from an industrial perspective, but from the perspective of organic synthesis, not so much. For the free radical halogenation, that is of importance. I'm just checking my timer here. That is of importance, and I want to spend a few minutes on that, because that does have value for the organic chemist. So, essentially, if I were to take, that's a good place to start, if I were to take methane, and I would expose methane to chlorine gas, for example, and I kept them in the dark, I'd have no reaction. So methane and chlorine in the dark, or at low temperature, nothing happens. But if I were to heat it, and that's typically about 350 degrees Celsius, or expose it to light, will I get a cascade of reactions that gives rise to monochloromethane, dichloromethane, trichloromethane, carbon tetrachloride, together with HCl. So in the cold and dark, there's no reaction. But if I expose the system to light or to heat, then what I get seems to be a sequential replacement of H's by chlorines, the substitution of H's by chlorines. So I get the first thing that appears is monochloromethane, then dichloromethane, trichloromethane, and then tetrachloromethane. So we want to have an understanding of how this happens. And what we know is that the reaction has 3 phases in it, 3 stages, if you will. The first stage is called initiation, and the initiation reaction is the one in which we take an intact molecule, in this case chlorine. So I'll start here. So there is initiation, and in initiation we take the intact molecule, the chlorine, and we crack it using heat or light. And this is a homolytic cleavage. You remember that when we talked about types of reactions? This is a homolysis. We are cleaving the bond to give rise to 2 like particles. In this case, I'll make 2 chlorine radicals. And the chlorine radical is just a chlorine atom, right? We're taking, functionally, the chlorine molecule, and we're cleaving it to generate a chlorine atom. And because the lone pairs are not of interest to us in this reaction, it reads a lone electron that does our chemistry, then we can pretty much kind of ignore the lone pairs because they're not really important in the chemistry. So fundamentally then, we are cracking the Cl-Cl bond and generating a radical, a pair of radicals. So this process in which an intact molecule undergoes homolysis, cracks, this bond cleavage, to generate a pair of free radicals, that's called initiation. Because that really is what begins the process. It's interesting that if I have, 10 million methane molecules and, a million chlorine molecules, when I shine light on the system, not every chlorine molecule will break. Not every one of them fractures into Cl and Cl. But as we've seen a little bit, I don't need them all to. I just need a few to initiate the process. Okay, so what happens next is that the Cl dots, once they're created, they are electrically neutral, which means they're not really attracted to anything in the system. In other words, if I have like when we did the corpuscle White House, we had a nucleophile and we had an electrophile. If you put a nucleophile and an electrophile in the same system, the nucleophile, because it's electron rich, is going to be sensing the electrophile, which is electron poor, and vice versa. So really in the matrix, they're moving towards each other based upon electrostatic interactions. So the nucleophile gravitates towards the electrophile, or vice versa, and we get connection, we get chemistry. Well, if you're electrically neutral, nothing is pulling you, right? You're going to bump into neighbors, but that's entirely random. So initially, what's in my container? Billions of methane molecules. Maybe billions of chlorine molecules. And of those, maybe a couple hundred of them fracture to give a couple hundreds of the chlorine atoms. So the chlorine atoms fly apart and start knocking blindly into things. So who will they encounter? Well, they'll encounter the container. Right? They're going to hit the container, rebound, back into the matrix. Who else will they encounter? Well, they will encounter other chlorine molecules. Right? So a chlorine atom will encounter chlorine molecules. Because what do I have in the system? I have chlorine molecules and methane molecules. So the statistical likelihood is that a Cl dot will encounter a chlorine molecule, and what we get is a reaction to give a chlorine molecule and a Cl dot. So although that happens, I don't really see it because my products are the same as my reactants. So it's not that it doesn't happen, I just don't detect it. Because from my perspective, nothing has changed. What I put in is what I get. Well, the next abundant species in the system are the methane molecules. So when a Cl dot bumps into a methane molecule, what it does is it abstracts a hydrogen atom and gives rise to HCl and CH3 dot. This is called a hydrogen atom abstraction. Right? Or sometimes simply H abstraction. In other words, I'm pulling away H dot. Right? I'm pulling away H dot. So you can imagine here, by the way, there are two electrons in this bond, and I've shown one electron going here. It stands to reason that the other one is going between this Cl and that Cl, right, to make the Cl-Cl bond. So one of these electrons is here, the other one is coming from this chlorine-chlorine bond. And it's not wrong to show this, it's just not necessary. So in the same way, this Cl dot attacks this H. One of these electrons, the one that H invested in the bond, comes here to pair with the H with the Cl's electron to give HCl, and the other electron goes back on the C to give CH3 dot. Now this step, these kinds of steps, and I'm going to ignore this one on the top because although it happens, I don't see it. But that's called a propagation step. This is called a propagation step. Because what happens is I am consuming one free radical, but making another. That's very different from this, where I have no free radicals, and I make two. That's why I initiate the process. Here, one free radical is consumed, and another one is created. Okay, now, is it likely, by the way, at this point, that a Cl, because the only other things present in the pot right after initiation are other Cl dots, right? I'm starting off with billions of this and billions of that, a couple hundred of these. So when these are born, the only thing they're seeing are chlorines and methanes. Now, the likelihood of them finding another Cl dot is remote. If I've only got a couple of hundred of these, because not all the chlorines are breaking up, if I've only got a couple of hundred of these, but billions of those, the likelihood of one of these running into another is vanishingly small. So I'm going to ignore that one for now. Okay, good. So the methyl radical is born. Good. Who does the methyl radical encounter? Well, again, it's not charged, so it's going to bump into things very randomly. It bump into the container. What particles in the system is it likely to find? Is it likely to find a Cl dot? No. There are only a couple of hundred of these in the pot. Is it likely to find another CH3 dot? No. There are very few of these in the pot at the beginning. The abundant species are methane and chlorine. So a CH3 dot will bump into a methane, abstract an H, and give rise to CH4 and CH3 dot. Well, that's the same scenario we had here. It happens, I just don't detect it, because my products and my reagents are the same thing. What I do detect is when a CH3 dot bumps into a chlorine. Because when it does that, I get CH3Cl and Cl dot. So now I'm seeing chemistry. And by the way, see, that's why this one shows up first. So there's an initiation and then a propagation step that gives rise to CH3Cl. So now what I'm going to do is we're going to describe, we've talked about this in some detail. I'm going to collapse it now into the things, into accounting for how I make product. So how do I make product? I'm just going to take all this off. How do I make my products? Well, there is my initiation step, which gives rise to Cl dot. Cl dot attacks methane in a propagation step, we get HCl and CH3 dot. And then the CH3 dot attacks chlorine to give rise to CH3Cl plus Cl dot. So the chlorine radical attacks the organic to give HCl and the alkyl radical. The alkyl radical attacks chlorine to give the substituted organic and Cl dot. Now remember, this Cl dot came from initiation. I consume one Cl dot and I generate another. So in fact, if I were to sum these two steps, what would I get? Well, the things present on the left and right, I'm going to cross them out. I'm going to cross that out. I'm going to cross that out. And the net reaction is going to be CH4 plus Cl2 gives rise to HCl plus CH3Cl. Give rise to HCl and CH3Cl. I sum those two propagation steps. Okay, so what happens? Well, eventually, the concentration, partial pressure, of CH3Cl rises to a level where it now begins to compete against its parent, against methane. So, a Cl dot is now likely to encounter a CH3Cl. The chlorine attacks the organic, gives rise to HCl and the organic radical. Right? Chlorine attacks the organic to give rise to HCl and the organic radical. The organic radical now attacks chlorine to give rise to the organic, the substituted organic, and Cl dot. Does that sound familiar? The organic radical attacks chlorine to give rise to the substituted organic plus Cl dot. And if I were to sum those two steps, so I'm going to cross out the things present on both sides. Right, so what I would get is CH3Cl plus Cl2 gives rise to CH2Cl2 plus HCl. Okay, so we're now seeing the presence of dichloromethane in the sequence. That only happens when the concentration of monochloromethane rises to a level where there are enough of them in the container that chlorine can start running into them. Okay? What happens next? How does trichloromethane show up? Well, not surprisingly, I'm going to go here. Not surprisingly, what happens next is a repeat of what we've seen before. Right? So the Cl dot, right? Look at it. The Cl dot attacks the organic. I make HCl and I make the organic radical. Then the organic radical attacks chlorine and gives rise to the substituted organic compound and Cl dot. If I add those steps together, then CH2Cl2 plus Cl2 gives CHCl3 plus HCl. By the way, CHCl3, in addition to being called trichloromethane, is also called chloroform. The last sequence, as you hopefully have picked up by now, Cl dot. Of course, when does this happen? When the concentration of trichloromethane, chloroform, rises to a level where it begins to compete with its progenitors. So the Cl will attack the CH, Cl3, abstract the H, give HCl, plus a trichloromethyl radical. The trichloromethyl radical reacts with Cl2 to give rise to tetrachloromethane, which is also called carbon tetrachloride.